So we had been doing all of this kind of very high abstract stuff. And I want to get away from the abstract stuff a little bit down to earth, but we're going to use the abstract, some of the abstract stuff anyway. So what we had proved is we proved that Euclidean eventually implies PID, which implies Noetherian, which implies unique factorization domain. Okay? So all I'm going to use is that for what I'm interested in right now, which I'll tell you in a second, is that the Eisenstein integers, so this is Eisenstein integers, right? W is e to the 2 pi I over 3, or satisfies w squared, let's see, w cubed is 1, so w cubed minus 1 is 0, and that factors as w minus 1 times w squared plus w plus 1. And w isn't itself 1, so it satisfies this equation. W squared plus w plus 1 is 0. Okay, so far so good? Thumbs up? Great. So, so this is the Eisenstein integers. And we were studying the Eisenstein integers for the same reason we were studying the Gaussian integers. So recall, wanted to know which integers n are represented as sums of two squares. And we answered the question using the Gaussian integers. Why? What do the Gaussian integers have to do with x squared plus y squared? Do we remember? You can type it in the chat, or you can unmute yourself and tell me. Norm, yes, exactly. Because the norm of an element, z, if z is x plus iy, then the norm, so this quadratic form, q of xy is equal to x squared plus y squared, is the norm form for the Gaussian integers. And that's kind of what made the whole thing work. So what is the norm form for an Eisenstein integer? You can type it in the chat if you remember. Yeah. Yep. Other than Depenger, does everybody remember that? We proved this a little while ago. The norm is x plus omega y times x minus omega y. Is that right? No. No, it's x plus omega bar y. Again, if omega is here, omega bar is here, the complex conjugate. Here's 1, the other cube root of unity. And we did this exercise, this calculation, that you get x squared minus xy plus y squared. Okay, so can we, having studied the Eisenstein integers, can we reverse engineer our question? So here's our new question. Which integers n are representable by this quadratic form? Okay, that was kind of the culmination of all of our hard work on the Gaussian integers, and now we're going to see what happens for Eisenstein integers. So remind me, did we talked about this like 3 weeks ago before break and before coronavirus and everything? So do we remember anything about these values? Should we make some table of values? Kevin, you're writing something? Oh, no. Should we see some? Okay, so let's look at some integers and see what we find. All right. Gosh. So let's make a little table of x's and y's. X is 0, 1, 2, 3, 4. Let's not go too high. 1, 2, 3, 4. So we can do this in real time. Can you see this? All right, if x and y are 0, the quadratic form q, this is, so we're looking at q of xy being equal to this thing. Okay, so what's the value for 0, 0? You can all type it in the chat. If x and y are both 0, then 0 squared minus 0 times 0 plus 0 squared. Yes, thank you, Sriya. All right, how about 1, 0? Actually, it's symmetric in x and y. Right, so 1 minus 1 times 0 plus 0 is 1. So that's also going to be 1. Okay, what else? How about 2, 0? What's this term? Four. Yep. And actually, when y is 0, all we get is x squared. So this is easy. This is going to be 9, that's going to be 16, and by symmetry, this is going to be 4, 9, 16. All right, so we definitely see the squares. That's good. What else do we see? How about 1, 1? 1 minus 1 plus 1, 1. How about 2, 1? 4 minus 2 plus 1. Right? Everybody sees that? Okay, good. Good, so we're getting 3. How about, so we get 3 here also. Now, 2, 2, this is interesting. 2, 2, that 2, because this is a homogeneous quadratic, so let's look at this square. It's a homogeneous, same genus, homogeneous quadratic form. Can you hear my kids in the background screaming? I'm going to tell them to quiet down. Quadratic form. So if you change from 1, 1, if you multiply both variables by 2, so that 2, 2, what factor comes outside?
Daddy,
guys, no, you gotta go right now. And stay quiet, please. Close the door.
And Daddy,
Close the door. Thank you. Interruptions. Where are we? Homogeneous quadratic forms. Yes, there's a factor of 2 multiplied by x and y. What will get pulled out is a factor of 4. Okay, everybody sees that. So whatever this was, this is just going to be 4 times that. And whatever this is, the 3, 3 entry, is going to be 9 times the 1, 1 entry. So that's a 9 and that's a 16. Okay? How about the 2, 4 entry? What's the 2, 4 entry related to? Can you explain that one more time? Yes. So the point is, if I multiply, so if I have q, let's see, there's no reason to skimp on paper. So the point is, q of kx, ky for any constant k is equal to, let's just look at what q is. It's k squared x squared minus kx ky, right? I take x squared xy plus k squared y squared. So because it's homogeneous, all the monomials are degree 2, and so there's a factor of k squared that pulls out of everything, and I'm left with x squared minus xy plus y squared, which was the original quadratic form. Alex, does that make sense? So if you know the value of one of these, so let's do this example. When x is 1 and y is 2, so q of 1, 2, we already worked out was 3. So q of 2, 4 has to be, I multiplied each of the coefficients by 2, So this is multiplying by 2. So what will happen to the value of the quadratic form? It'll multiply by, right, exactly, Sriya. It'll multiply by 4. So you get 12 here. So I automatically know that the 2, 4 entry is 12 without doing anything. Does that make sense? So actually, all we really need to know is what the values are on the primitive integers. But all right, let's come back to that. Let's just make sure that it really is 12. So when x is 2 and y is 4, 2 squared is, whoops, you can't see that. When x is 2 and y is 4, I get a 4 plus a 16, 2 squared plus 4 squared, 4 plus 16, 20. And I subtract off 4 times 2, subtract off 8, that makes 12. Karen, you have a question. Can you unmute yourself and ask, or do you want to type it?
Can you hear me?
Yes.
Oh, okay. How did using the norm function x squared plus y squared, sorry, I'm taking us back a little bit.
Yep.
How did that solve the question of which n is equal to x squared plus y squared?
Yeah. Great question. I'm gonna review that in another second, if that's okay. Just to remember how it was that we used the Gaussian integers to get at this question. There was, well, let me review it right now quickly, and I'll review it in more depth because we're about to do the same thing on the Eisenstein integers. But the first thing to remember is that we saw that there was this congruence obstruction. So if a number is 3 mod 4, it's never a sum of 2 squares. And the other thing was that every prime that's 1 mod 4 can be expressed in this way, and that's because you have unique factorization in this ring, and we use that unique factorization not only to show that every prime could be expressed as a sum of 2 squares, but to actually find efficiently that representation.
Oh, okay.
Does that ring a bell? I'll review that. It's been a while since we saw that argument. But the same exact thing is going to happen here. We have this other quadratic form. It looks like a weird quadratic form, but actually it's the norm form for a nice ring with unique factorization. And so it's going to have all the same nice properties of, you can solve efficiently the question of which primes are represented by this. And then given the primes, once you know what happens on the level of primes, you can do the same thing on the level of all numbers.
Okay, thank you.
My pleasure. Kevin has a question. If it's faster to just say it, you can unmute yourself. Oh, how do you unmute yourself? Let's see. Can you, it's not showing to me that you are muted. Bottom left button. Right, there's the leave audio button and a video. Leave audio, then reconnect. If you entered only as a listener, you can't talk at all. Oh, I see. So there's an option when you enter to join just as a listener or as a speaker?
Hello?
Yep. Oh, great.
Okay.
You unmuted yourself. Great.
Okay, one question. It's with the kx and the q of kx and ky thing.
Yep.
We use that to show that 12 is just like 4 times 3 again.
Yeah. So the point is, this q of, if x is 1 and y is 2, then
Okay.
all I've done is doubled both of them. I doubled x and I doubled y.
Okay.
So I multiplied each by a constant k.
Okay.
And q, the value that q takes on a multiple of 2 on both variables, is to square that multiple and take the original value.
Okay.
So the original value was 3.
Oh, okay, I see.
Yeah? And it's, it's really important that we keep doing this where anytime you have any kind of question, please, please, please ask. Kevin, I guarantee there are 3 other people, 10 other people, 20 other people. I don't know how many people were confused about this and just didn't bother asking. So it's very good that you ask, and please keep asking. Okay? Does that make sense? So the point is we doubled all the entries. That means the answer is going to 4-tuple instead of doubling. And that's always the case. If we triple the answers, then if we triple the entries, then the answer is going to multiply by
4.
if I multiply. So what is Q of 3, 6? I tripled.
9.
Yeah, it's going to multiply by 9. So it's going to be 9 times 3, which is 27. Okay, does that make sense? That's only the case when there's a common factor or they're equal. It's the case when the polynomial is homogeneous. Anytime each monomial has exactly the same total degree. Does that make sense? So if the total degree, this is going to change by a factor of k squared, this is going to change by a factor of k squared, and this is going to change by a factor of k squared. So that k squared pulls all the way out. If I didn't have a quadratic form, if I had just, some other polynomial, I meant, is this for a specific question, x, y must have a common factor? I meant for this specific question, x and y must have... Yes, if they don't have a common factor, 1 and 2 don't have a common factor. So there's nothing we can do except plug in the values. But if they do have a common factor, that common factor pulls out as a square, and then we're left with the value, the original value. So that's why sometimes people only care about the primitive values that a quadratic form takes, because the imprimitive values, so... we're going to come into that discussion in a minute. What integers n does it represent primitively or imprimitively? Alex, did I answer your question? Great. Okay. So let's just keep filling out our table, see if we start seeing patterns of what numbers we are seeing, what numbers we aren't. So we're seeing 3, so it's definitely not numbers that are 3 mod 4. There's something else going on. What I mean is 3 mod 4 was missing from the sums of 2 squares. It's not missing here. How about 1, 3? Can we use any trick to evaluate 1, 3? No, they're coprime, so all we can do is go back into this equation. So if x is, let's do it here. If x is 3 and y is 1, I get 9 plus 1 is 10, minus 3 times 1 is 3, so 10 minus 3. Yep. Okay, so we have 7 here, and we have 7 here. This is because of the symmetry. Q of xy in this case happens to be q of yx. How about 1, 4? So 4, why don't you guys write in once you have the value of 1, 4? Take a second, make sure you're following along. What am I about to write here? Okay, I'm seeing a couple 13s. Let's see if I agree. 4 squared is 16, plus 1 squared is 17, but then I take away 4 times 1, so 17 minus 4, 13. All right, so we're seeing 12s, 13s, 16s, 7s, 9s, 4s. How about 2 and 3? What's this entry? Sriya's going to tell us. Chang. Sriya says 7. So does the Bendro. Okay, let's see why it's 7. 3 squared is 9. 2 squared is 4. 9 and 4 is 13. And then 2 times 3 is 6. So 13 minus 6 is 7. I agree. So that means this also gets a 7. So 7 is represented in 2 different ways. That's kind of funny. As 1 and 3 and as 2 and 3. Okay. How about 3 and 4? The 3, 4 entry? I guess I haven't been putting all of these in. We had a 13 here. We had a 12 here. We only have one more entry until we've done our 4x4 table for Q. So 3, 4. We're getting another 13. 16 plus 9 is 25, but 3 times 4 is 12. 25 minus 12, I also get 13. All right. Everybody see that? Can I get a thumbs up if you understand what this table is doing and some of its properties? Awesome. Any questions? Stephanie's typing. Do you want to unmute yourself and ask? Oh, no question. Okay. Accident. Okay, no problem. Great. So what numbers are we seeing? So the ends, we are seeing ends represented by this quadratic form. They're all in the set. What did we? Well, of course we can represent 0. That's kind of cheating. 1. We don't see any 2s, curiously. We're not seeing 2s. We're seeing 3 and 4. I don't see a 5. I don't see a 6. I see a 7. A couple of ways I see a 7. I don't see an 8. I do see a 9. Am I missing anything? I see a 12. I see a 13, and so on. Okay, does everybody see that? So these are the numbers that we're observing. Now, with sums of two squares, with x squared plus y squared, it was clear that the numbers that you see get bigger the farther out you go. The farther out you go. Right? Because it's a sum of, sorry, you can't see. So it's a sum of squares. So the larger I make x and the larger I make y, the larger the sum of squares is going to be. How about this? How about this? What about x squared minus xy plus y squared? Well, there's a minus there. So maybe there's a way to make kind of large negative numbers out of this. What do you think? Can this take, for example, negative values? Negative values. No, because it's a norm. That's right. That's a very good point. If we didn't know a priori that it was a norm, is there some other way to see that it can't take negative values? It is a sum of a square, right? Okay, so great. We're getting a lot of good suggestions. So Daniel's suggestion is to observe that this is equal to x minus y squared plus xy. So let's see, x minus y squared would give me an x squared plus a y squared minus 2xy plus another xy gives me a minus 1xy. So I agree with that. So if you make x and y large numbers, this number is a square. If we're making x and y positive, then this number is what's the word I'm looking for? Large. So if x and y are positive, it's clear that this thing's always positive. Now maybe I can make x large positive and y large negative. So I don't immediately see x squared and y squared are always positive and xy is never greater than both. Right, and which is what Yukong is saying as well as Alex. Here's a way that you can kind of, this will bring you all the way back to high school or middle school or something. you can turn, so to see this for a general form, to see this in general, for example, 7x squared minus 32xy plus 12y squared. Now what? Does it take both positive and negative values? Only positive values? Only negative values? Does this take large, small, positive, negative values? So how can we tell? Karen? You can have negatives because at 1, 1, very good. At 1, 1, if x is y and if x is 1 and y is 1, then we get 7 plus 12. That's nowhere near big enough to count this negative 32. All right. So here's a trick. If I pull out y squared, so here's the trick. It's not a trick. It's an idea. Idea is a better word. Idea. Pull out y squared. So let's pull it out of this form. What I get is y squared times, well, how do I pull a y squared out of an x squared? I don't have a, no, because the norm, a quarter times that would work. It would be a miraculous if that were the case, because I just kind of made this up. Most quadratic forms are not norm forms. Did you try it, Dipendra? Does it work? Oh, for the Eisenstein. Yes, that's right. That's right. For the Eisenstein, you factor out a 1/4, and it looks like 1 plus 3 x squared plus 3y squared after I change the variables. We're going to come back to that issue. Yeah. That's a really good point. We're going to come back to that point. So let's pull out a y squared from here. The point is I don't have a y squared, so I just have to write x squared over y squared, which let me write as x over y squared. Right? How about here? I'll pull out a y squared. I have just a y, so I get an xy over y squared. That's x over y. And then I pull out a y squared, and that's a 1. So I have dehomogenized, instead of getting a homogeneous polynomial. So if we set z to be x over y, which now can be any rational number. This is just an arbitrary rational number. X and y are arbitrary integers. So this is a square times then q of xy is equal to a square times, is it okay if I still write this as q of z, where q, instead of being a quadratic form, is now just a quadratic polynomial, z squared minus z plus 1? Does that make sense? Can I get a thumbs up if it makes sense what I did? So you can think of q as a quadratic polynomial, or you can think of q as a quadratic form. Yeah? And the only distinction between the two is whether you make it homogeneous or not. So you can dehomogenize and you can homogenize. Okay? But what's the graph of this thing? Well, it's a parabola. Right? It's a parabola. It's an upwards facing parabola. So this q of z is an upwards facing parabola. So either it looks like this or it looks like this. This would mean it only takes positive values. This would mean it takes both positive and negative values. And those negative values can become very large if it's multiplied by a large square. Right? This is always non-negative. And so the question is, which is it? Is our q this or this? Question mark. How do you tell? How do you tell, given a quadratic form, not a quadratic form, a quadratic polynomial now, whether it has real roots? Now we're back to high school. Middle school. I don't know when you learned this. Yeah, quadratic formula, plug in 0, right? Set it equal to 0 and solve. The quadratic formula will tell you, yes, Kevin, the discriminant. Remember, so if we try to solve, so let's use all of the ideas that you guys put in there. If we try to solve q equals 0, so in this case it's z squared minus z plus 1, well, we can always solve it by the quadratic formula. That means z is equal to negative b plus or minus square root of b squared minus 4ac over 2. How do I know x over y is in q? Well, if x and y are integers, then x over y is irrational. That's all I mean by this. But the point is, if it takes rational values, then now it takes a dense set of values. So we may as well look at it in the reals. Does that make sense, Karen? We've gone from integer values of q to now looking at real values of q, not even rational values of q, because now I'm drawing a curve instead of plotting a million points. Okay? So it's exactly this, the discriminant of the quadratic form is telling us whether or not it has real roots. So can I get a letter A if you think that our form takes positive and negative values, or a letter B if you think it only takes positive values? Awesome. Awesome. Everybody sees it, right? The point is this discriminant, so this would, for a general form, let's write q is equal to bracket ABC, by which I mean either ax squared plus bxy plus cy squared, if it's a quadratic form, or this can mean, depending on context, ax squared plus bx plus, let's call it z, az squared plus bz plus c, if it's the quadratic polynomial corresponding to the quadratic form. So I'll write ABC for either. Let's write this out. We'll use this notation for both. Maybe abuse is the right. We'll abuse notation and use ABC for both the quadratic polynomial and the quadratic form. Okay? And so now you know about quadratic forms, because you can always pull out a y squared to get down to a quadratic polynomial, and that quadratic polynomial, so q takes both positive and negative values if and only if it has roots. If the quadratic polynomial has roots, which means b squared minus 4ac is positive. We'll deal with what happens if it's 0. If it's 0, then there's a double root, and actually the quadratic form splits. So let's not think about that right now. Sorry, your internet and laptop died. That's okay. Sarah, you're back? Is Sarah here? Yeah, okay. Should I go back to anything, Sarah, or everything's okay so far? Okay, great. So, for our form, this discriminant, so this is of course the discriminant, for our form, well, we keep changing which one is ours, but the Eisenstein form, q equals x squared minus xy plus y squared, the discriminant discriminates between these two pictures. The discriminant, b squared minus 4ac, is negative. It's negative 3, in fact. The discriminant is negative 3, which is negative. Oops, there we go. so the quadratic form only takes larger and larger positive values. Right? You can't see both at once. So the quadratic form, so Q only takes larger and larger positive values. Okay? Can we discuss how we got the quadratic form? You mean the general quadratic form, Sheik, or how we went from the quadratic form to the quadratic polynomial? You can unmute yourself if you want, Sheik. The quadratic polynomial. Yeah, so this is dehomogenizing. I'm just setting, if you like, set y equal to 1. That's another way of looking at it. So the quadratic polynomial is, let's see, this is q of z comma 1. The reason this works is I'm really thinking in projective space, but I don't want to talk about projective space now. So this is dehomogenizing. So if you take a quadratic, maybe think of starting with a quadratic polynomial and make it homogeneous by adding a variable of the appropriate degree. What does dehomogenizing mean? Okay, dehomogenizing, homogenizing is a well-defined thing. So let's aside, make. I'll give you a polynomial: x cubed plus 4 x squared y squared minus 5 xy. Make this homogeneous. How do you make something homogeneous? It's not homogeneous. What am I supposed to do? So to make it homogeneous, I add a new variable, add an auxiliary variable. Auxiliary, how do you spell auxiliary? I-A-I-R-Y? Anybody? Yeah. Oh, no I. Okay, thanks. Auxiliary variable. What do you want to call it? Z? W? Anybody? J? Q? Z? Kevin says Z. Let's say Z to make all monomials. The monomials are the pieces that are being added together. Make all the monomials have the same degree. Have the same degree. Okay, so what's the total degree of this? Total degree, which means the largest degree. Can everybody write in what the total degree is? Yep. You see 4. This is degree 4, this is degree 3, this is degree 2. So total degree equals 4. Oh, I was right with the I? All right. So I was right after all. Anyway. 1L. Oh, 1L. That's what it is. Really? All right. Anyway, you guys will give me a spelling test later. Kevin, were you writing more? No, just 1L. Maybe that L looks like an I or something. All right, whatever. The total degree is 4. So how do I make this? So not equals, but gets converted into. How do I make this have degree 4? I have this extra variable, z. What can I do with that extra variable? Yes, multiply. I can't multiply by x. That genuinely changes the polynomial. But I can multiply by another variable, which is my auxiliary variable, which is z. So I can replace x cubed by x cubed z. What do I want to do with the x squared y squared? Okay, where are we? We're doing some hard stuff. I didn't mean to be doing the hard stuff. I don't know why I keep getting sidetracked with the hard stuff. I keep meaning to do very simple things that are very computational instead of going into very complicated things. We're going to finish homogenizing this polynomial, and then we're going back to regular old easy stuff. The point is, I'm going to add a variable to the right exponent so that all of the monomials have the same total degree 4. So this one I don't have to do anything to. It's just x squared y squared. This one I have to do something to. To raise this up to degree 4, I have to multiply it by a factor of... I have this auxiliary variable z. Yes, z squared. Exactly. Okay? So that's what it means to homogenize a polynomial. And dehomogenize, well, there's a variety of ways of thinking about it, or dehomogenizing this thing. But one way is to set one of the variables to be 1. Okay? So to get back to the original polynomial, to get back to the original, which is what I'm calling dehomogenize, which is not standard nomenclature, set z back to 1, get rid of it. Okay, does that make sense? Kevin, do you want to ask something? Unmute yourself.
Yeah, I just have a question.
Sure.
You're multiplying each like monomial by different things. So how do you like guarantee like equality or?
So I'm not guaranteeing any kind of equality. I'm completely changing the polynomial. So this is a new polynomial, which is a polynomial in 3 variables. And the only observation that I'm making is that if I look at the slice through this polynomial when z is equal to 1, I recover the original polynomial in only 2 variables.
Okay.
So this is also called projectivizing, homogenizing or projectivizing. Because this is in projective space. Never mind. So this is maybe deprojectivizing, undoing that thing. So that's what's really going on. That's the reason it's useful to look at the quadratic polynomial instead of the quadratic form. Well, because it only has 1 variable, so then it's easy to think about what happens to a 1 variable polynomial. You can just graph it. As opposed to 2 variables, well, now there's some surface. You know, if I want to look at the values, how do we even look at the values of that? There's some surface. Z equals this thing. I mean, that's the surface. Does that kind of make sense? Let me just say that again. The values, the real values taken by Q. Let's stick to our let's be kind of back down to earth. Taken by our quadratic form are, well, they're the solutions whenever z is equal to x squared minus xy plus y squared. But that's one equation in 3 variables, so we can graph that. That's some kind of surface, and I don't know what it looks like, but it looks like some kind of, this is not touching the ground, this is off the ground. Well, actually, it is touching the origin, because when x and y are both 0, then z is 0. So that's touching the ground, and then it's this kind of curvy thing. Okay? So that's what this one looks like. And if it had a different discriminant, then it would look different. Then it would have positive and negative values. And in fact, it would look like a 2-sheeted hyperbola instead of 1-sheeted. Okay. I'm getting ahead of myself. All I want to do right now is understand the integer values of this thing. So the question is, at what heights? So if we look at the integer points x, y, z, if we look at just the integer grid of x and y, of course z has to be integers. The question is, what heights have integer points and what heights don't have integer points? And so in our table, all the way back here, what were we talking about? I was trying to make the point that you can see these values, the values of the quadratic form. So for example, 1, 3, 7 would be x equals 1, y equals 1, 2, 3, and they would meet at height 7. So this is the point 1, 3, 7, where z is equal to 7, and that's the value of the quadratic form when x is 1 and y is 3. Okay, so this point, graphically, is this point. Does that kind of make sense? So we're kind of This is the way to see this as a surface in real space. Can I get a thumbs up if this is making any sense? Yeah? Thumbs up. Is there anyone who's okay. If you are confused about this, I'm just trying to it's okay. I don't even know what I'm trying to do at this point. I'm just trying to get through the next 20 minutes without it crashing again. So let's go back. What are we doing? Back to our question. Our question is what values does q equal to x squared minus xy plus y squared take? And the answer, well, at least some values that we already saw, it takes the value 0, 1, 3, 4, 7, 9, am I missing anybody? 12, 13, 16. And you can kind of see already here why this thing is a surface, right? We're plotting this corner of it, the 4 by 4 corner, and the values start out small and they get larger and larger. So that's kind of this view here. And if we took negative values, we would get we would get kind of the back half of this. We're only seeing kind of this bit of the surface. Okay. So do we notice any patterns? Notice any patterns? What numbers are not represented here? Without more data, I think it's pretty hard to notice patterns. Dipendro? Let's look mod 4, by the way. Do we see everybody mod 4? I see a 0 mod 4. I see a 1. I see a 3. If we go out a little further, we'll see a 2 mod 4. It turns out 4 is not the right modulus here. Yeah, we haven't seen a 2 mod 4, but I think we will soon. Is 18... No, but is 22? No, 26? Mod 5? Mod 5 is another good guess. I'm seeing 0, 1, 3, 4, but not 2 mod 5. Well, here's 2 mod 5. So I'm seeing all the values mod 5. Yeah, so let's write this down. Mod 5, the values that we're seeing are 0, 1, 3, 4. Mod 5 is 2. Mod 5 is 4. So we've already seen all of them. So all values. Mod 4, we haven't seen all of them yet. I guess there's a good reason why we're not going to see 2 mod 4. Yes, because W is a third root of unity. Something funny is going to happen mod 3. Let's look mod 3 at these values. And I'll explain why we won't see 2 mod 4, but it's because of because mod 3. Right. So let's look at all of these. What are the values mod 3? I see a 0, I see a 1. This is 0, this is 1. 7 mod 3 is... If you guys want to write it in. Yep, 7 is 1 mod 3. 9 is 0 mod 3. 12 mod 3 is 0. It's a multiple of 3. 13 is 1 more than that. 16 is 1 more than 15. So we're only seeing zeros and ones. That's a pretty strong pattern. That's a pretty strong pattern. So that suggests a conjecture. What's the conjecture? What value mod 3 don't we see? Conjecture. That this quadratic form never takes the values altogether Yeah, doesn't take the value 2 mod 3. Now, fortunately, this is a very easy conjecture to prove, because all we have to do is look at the values of x and y being 0, 1, or 2 mod 3. 0, 1, or 2. Okay, which, by the way, we've already done without taking mod 3. So it's just these values mod 3. So we don't have to do a lot of extra work. I'm just going to rewrite these values, but take the mod 3. 0, 1, 1, 1, 1, 0, and then it's symmetric. So 1, 1, 0, and then this value is 1. Wait, what does w being a third root of unity mean? It just means that w cubed is 1. Being a root of unity means, like, you know, you might write w cubed is 1, so w is 1 to the 1/3. It's a cube root of unity. But, of course, this is 1. It's a non-trivial cube root of unity. It's a number whose cube is 1. That's all that means. Okay. So you should think about 3 as interacting in that way. So the point is the values of q only takes 0 or 1. So because this form q only takes 0, 1 mod 3, it will never, there are no integers, so we just proved the theorem. This conjecture is now a theorem. For all integers x and y, x squared minus xy plus y squared is not equal to 2 mod 3. Okay? Now let's look at 1 mod 3. So let's see if we can finish this part of the discussion. So I claim every prime congruent to 1 mod 3. So primes are either 1 mod 3, or they're 2 mod 3, or they're 3 itself. And 3 itself is a value, so 3 is represented. And now let's look at primes mod 3. My claim is that every prime congruent to 1 mod 3 is represented, claim for every prime congruent 1 mod 3, there exists integers x and y such that x squared minus xy plus y squared is equal to p. Okay, so i.e. all primes congruent to 1 mod 3 are represented. Okay, so my claim is the only obstruction, at least on the level of primes, is being 2 mod 3. And we can see, so who are the primes that are 1 mod 3? 4 is not a prime, 7 is a prime, and 7's there. 10 is not a prime, 13 is a prime, and it is there. Who's the next prime that's 1 mod 3? 18, 19. 19 had better be there. Can we figure out how to make 19? So if the claim is true, if the claim is true, then 19 can be written as x squared minus xy plus y squared. Can we find an x and y that makes this happen? How to find x and y. And in the process, we'll prove that x and y exist. Sriya, you want to say? Oh, you already got it, Dipendra. 3 and 5. Okay, let's see 3 and 5. 3. Okay, so people are trying 3 and 5. So q of 3, 5 is equal to 3 squared is 9, 5 squared is 25, 9 plus 25 is 34, 3 times 5 is 15, 34 minus 15 is 19. Great. Great. Dipendra has another one. 2 and 5 also work. Let's see. So this is equal to 19. That checks out. Q of 2 and 5, Dipendra is saying, will also work. That's 4 plus 25, 29, minus 10 is 19. Yep. Great. Great. Why does this not work for 10, since 10 is also 1 mod 3? Ah, great question, Sriya. 10 is 1 mod 3, so 10 which is 1 mod 3, but 10 is equal to 5 times 2. And both 5 and 2 are 2 mod 3. So the reason 10 is 1 mod 3 is it's the product of two primes that are 2 mod 3, and neither of these have a representation, and so 10 also doesn't have a representation. I haven't proved that for you. I'm going to prove that once you know what's going on the level of primes, you know what's going on everywhere. Sriya, does that make sense? Okay. Great. So it's not just about numbers being 1 mod 3, it's specifically about primes, because a number can be 1 mod 3 even though it's made up of primes that are 2 mod 3, if there's an even number of those primes. Okay. Let's find these two solutions. Let's find them in a very similar way to what we did for the sum of two squares and the Gaussian integers. So, recall Fermat's little theorem. We'll say that a to the p minus 1 is congruent. So, if a is not congruent to 0 mod p, then a to the p minus 1 is congruent altogether now. Mod p. Everybody remember this? You take any number, you raise it to the p minus 1 power, you get 1 mod that prime. Does that ring a bell? Yeah. Okay. What about, so if p is congruent to 1 mod 3, then a to the p minus 1 over 3 makes sense. Makes sense. This is an integer. So this whole thing makes sense. Right? You can raise any number to the p minus 1 over 3 power, because p minus 1 over 3 is an integer, because p is 1 mod 3. Wait, what did we do? Yes, we did something exactly similar. With p is 1 mod 4, we looked at a to the p minus 1 over 4. That's exactly what I'm mimicking. Yep. Recall for p equivalent to 1 mod 4 and x squared plus y squared, we looked at a to the p minus 1 over 4. Okay, is this ringing bells? So let's look at what happens to this. Well, this makes sense. So set z equal to a to the p minus 1 over 3. This is some number. This is some number mod p. This number has a funny property. What is z cubed mod p? Karen, good guess. You're very close. We want the multiplicative inverse, multiplicative identity, not the additive identity. Yep. Does everybody see that? Does everybody see? Karen, why are you saying that this is equal to 1? You're absolutely right. You can unmute yourself if it's easier to describe. Karen, can you, we can't hear you. Yes, now we hear you. Or at least I hear you. Go on.
Just z take the 3 out of the denominator of the exponent.
Exactly. Z is p minus 1 over 3 cubed. So this is a to the p minus 1, which we just said was 1. Right? Exactly as Karen said. Everybody see that? So wait a second, this is a number whose cube is 1. It's a modular number that behaves like omega, like this cube root of unity. If we can find an a such that z equals a to the p minus 1 over 3 is not itself 1. We don't know. So Dipendro's asking, Dipendro's question is, how do we know z doesn't act like z could be 1 itself? If we can find an a so that a to the p minus 1 over 3 is not itself 1, then z is not 1, but z cubed is 1. And that's going to start off a chain of events. So let's see how likely or unlikely is it to find such an a. How likely are we to find such an a? All right, let's do this experimentally. Example. Let's go back to p equals 19. Okay, this is our prime. 19 is 1 mod 4, 1 mod 3. Okay, and what is p minus 1 over 3? 6, perfect. So let's take a bunch of numbers. A could be, well, it could be 0, but we don't care about 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's enough for now. And we're going to raise it to the p minus 1 over 3 power. In other words, to the 6th power. Okay, so 1 to the 6th power. All together. Yep. 2 to the 6th power mod 19. So remember, okay, so let's work out 2 to the 6th. 2 to the 6th is 2 to the 4 times 2 squared. 2 squared is easy, that's 4. 2 to the 4 is 4 squared, 16. 16 mod 19, it's too hard to multiply 4 by 16 and reduce mod 19. So I'm going to replace 16 by something else mod 19. What's 16 the same as mod 19? Let's be really lazy. Do as little work as possible. Negative 3, awesome. 4 times negative 3 is easy, that's negative 12. And negative 12 mod 19 is the same thing as 7. Okay, so 2 cubed, wait a second, 2 to this power, 2 to the 6th power is 7. What's 7 cubed? Let's just test out this theory. What's 7 cubed? 7 squared, I don't see an easier way to do that. 7 squared is 49. 49 mod 19, I can take out 38, and I'm left with, yeah, I don't want to figure out what 343 is mod 19. That's too hard for my brain. But 49 mod 19 is still a little hard, but I can see that 38 leaves a remainder of negative 8. Right, 11, which is negative 8, exactly. And so if I want 7 cubed, 7 cubed is 7 squared times 7, so that's negative 8 times 7, that's negative 56. Okay, you got it already? 56 is, I can add 38, I can do better than that, right? I can add, what's 19 times 3? Wait a second, 57 is a multiple of, yeah, 57 is a multiple of 19, and so negative 56 is 1, because it's 1 more than negative 57. So 7 cubed, this is a number whose cube is 1, but it itself is not 1. Does everybody see that? Let's write that down. We already, before, we were going to try a whole bunch of numbers, we found we have succeeded in finding, we have found z equals 7, which is 2 to the 19 minus 1 over 3. I mean, it's congruent to that. With z cubed being 1 mod 19. Does everybody see that? Let's just keep going a little bit to see how unlikely that was. So what's 3? Let's work out a couple more things. 3 to the 6, 3 to the 4 times 3 squared. 3 squared is 9, nothing we can do with that. 3 to the 4 is 9 squared. 9 times 9 is 81. How many multiples of 4? How many multiples of 19 can I take out? I think I can take out 4 multiples. 4 multiples. So this is 9 times 81. But 81 is, what's 81 mod 19? 5, I want to say. I think this is 5 mod 19 because 19 is basically 20, and 20 times 4 is 80, but I don't actually have 80. I have 4 less than 80 because I did 19 times. Okay, if that arithmetic is a little too cumbersome for you, just do the long run. So 76 is 19 times 4. So this is 5 plus 76, and 76 is 19 times 4. Okay, that's all I'm saying. That's how I got that 5. I hope I did that right. So this is 45. 45 is 38 plus 7. Did I get that right? Can everybody give me a thumbs up if you follow what I'm doing, and a thumbs down if you if you couldn't do this on your own? Okay, bunch of thumbs up. Great. So 3 to the 6, 3 to the 6 is also 7. How about 4 to the 6? Well, 4 is 2 squared. Go ahead, Kevin. How did I get the 45 is congruent to 7? This is all mod 19. That's because 45 is 38, which is 2 times 19, plus something, and that something is 7. And 38 is 2 times 19. Okay, we're out of time. I'm going to leave you an exercise, and it's just a computational exercise, just one exercise. Fill out this table. Fill out this table. So a versus a to the p minus 1 over 3 for a going from 1 up to p minus 1, I guess. And p equals, whoops, you can't see. And p equals 19, which is the one we were working on. And let me give you one more. What's the next prime that's 1 mod 3? 21, 22 is not prime. 24, 25 is not prime. 27, 28 is not prime. 31. And p equals 31. So these are two tables. One for p equals 19, one for p equals 31. If you don't want to do it by hand, go ahead and program it. I don't mind. I'm just curious to see a pattern of how likely is it to find a solution to this problem, find a number whose cube is 1, which itself isn't 1. And then next time we're going to see how to use that to write the number p, which is 1 mod 3, as a sum of, well, as a norm of an Eisenstein integer. Okay? Any questions?